So we're going to start by talking about the equilibrium constant of an acid. And for the example that I'm going to give, we're going to look at acetic acid, which is the acid that you're looking at in your lab. Acetic acid or ethanoic acid has an equilibrium constant of 1.8 by 10 to the minus 5. We're going to use this to try and predict what the pH would be. We start with 0.5 molar of acetic acid, CH3COOH, or ethanoic acid, and we want to find out what is the pH of this solution. And we do know one thing from that table: the Ka of the acid is 1.8 by 10 to the minus 5. And normally the Kas aren't given units, particularly in tables, but if you wanted to work out what the units were, then you'd find out that they were actually moles per litre. So the equilibrium equation for this acid is the ethanoic acid, which then turns into the hydrogen, or the H plus ion, and the acetate ion, CH3COO minus. And we can look at that and go, okay, well, what happens? I like setting it up as a table because this follows through to when you start looking at buffers. So initially, we have 0.5 moles of just acetic acid, and no hydrogen ions and no ethanoate ions. Obviously, this is an ideal sort of situation. This is basically when you make it up from a solid or from a very concentrated solution. You're making it up, and before it gets diluted, before it dissociates, it's zero. So what is it at equilibrium? Well, in between, there's a change. So there's a change of what? Well, this acetic acid dissociates a little bit, so it loses a little bit, and we're going to call that little bit X. Because it loses a little bit, this means that the bit that it loses turns into hydrogen ions, so it's going to have positive X, and also acetate ions, so positive X. So our change is minus X on this side and plus X on that side. The equilibrium is therefore 0.5 minus that little bit, and here we've got plus a little bit, so plus X and plus X. And this ICE ends up being ICE, so if you like having mnemonic devices, ICE, initial change equilibrium. It's a really good way to set things out. Why? Well, you can see how all your concentrations change. So we can set up a equilibrium equation for this. Our Ka in this case is going to be the products, H plus, CH3COO minus acetate, over the acetic acid, CH3COOH. And those square brackets mean concentration. So we substitute in the values that we have. We have X and X, so X times X, all over 0.5 minus X. So that's X squared over 0.5 minus X. And we can make a very neat assumption. If we make the assumption that X is much, much less than 0.5, then we can kind of reduce this value here approximately to X squared on 0.5. Now, if that assumption doesn't hold, then we have to use the quadratic equation. So we're going to have to multiply everything out. But if it does hold, meaning that we have this rule called the 5% rule. So if this is okay and this is less than 5% of this value, then we can make this assumption. And if we make that assumption, then it makes the maths easier. That's the whole reason why we do it. So we want to find out what X is. So we have Ka equaling X squared on 0.5, and Ka we know is 1.8 times 10 to the minus 5. So I'm going to multiply that out. X squared is equal to 0.5 times 1.8, so that's half of, say, 18, which is 9 times 10 to the minus 6. So that means X is the square root of 9 times 10 to the minus 6. So the square root of 9 is 3. 10 to the minus 6, I'm going to divide that by a half, that factor, so it's going to be times 10 to the minus 3. So what does that mean? X. Well, what does it really mean? We look back up at this table here and we go, okay, that X is our hydronium ion concentration, so H plus. So we now have a concentration of hydrogen in the solution. So we can use pH equaling minus log of the H, and we get a value for pH, minus log of 3 by 10 to the minus 3, which is going to be around about 2.52. So the pH of this solution, 0.5 molar of acetic acid, is going to be 2.52, approximately. Let's just test this assumption. Is this assumption correct? Well, let's see. We have 3 by 10 to the minus 3 was our x, and we're going to divide that by 0.5 and times it by 100. And that gives us 0.6%. So 0.6% is much, much less than 5%, which means that basically our x, which was 3 by 10 to the minus 3, is much, much less than 0.5. So we can use this assumption. There may be times when you can't use that, and then you have to multiply out and use a quadratic formula. But in most cases with the weak acids, this assumption holds true.